this one first. Okay, so what we are going to do next is, all right, we're gonna do some calculations here using all of the stuff that we introduced last time about the electric field, lead to electric forces, and from understanding those two, eventually we derived the Coulomb's law, right? The force between two particles that have charge on it. So with all those, we're going to be able to be sort of like solve a lot of problem when you have distributions of point particles with charge on it. Okay, so let's take a look. And I think this is a good exercise to reveal what we have been doing. So in the figure, 3 charged particles lie on in x-axis. Okay. Particles 1 and 2 are fixed in place. Particle 3 is free to move. So it means the number 3 is pretty much like you can, move around or place anywhere you like. But the information is here. But the net electrostatic force on it from those first 2 particles happens to be 0. Given that if the distance L12 and L23 are the same, what should be the ratio of the charge on on particle 1 and 2? You want to give it a shot? Yeah? All right, but I think you guys sort of like get an idea of what we are trying to do here, right? So the information is at the location of particle number 3, there is no electrostatic force. Okay, so when they say something like this, one way to think about this is think about what is the force on 3 due to particle number 1. And then you look for what is the force on 3 due to the particle number 2. And those 2 forces must cancel themselves out. Does that make sense?
Okay.
Okay, so that's what we are trying to do here is just think in terms of the force. Okay, let me try to do that first. Now, because you don't have any information about the charge type, you don't know is it positive or is it negative, but it doesn't really matter because you want the cancellation. So what I'm saying over here is if you want cancellation, what does it mean? If you assume that charge number 3 is positive, and then charge number 1 is also positive, the force that acting on charge number 3 due to the charge number 1 will be pointing to your right side. Does that make sense to you? Okay, follow this, yeah? And now because you want another force to cancel this one, so you want a force that is pointing to your left. And that pretty much force the charge number 2 must be a negative charge. And that will lead you to an attractive force due to the charge number 2 to your left side. Does that make sense? All right. However, some of you might just say, well, John, if I said my charge number 3 is negative, okay, and charge number 1 is negative as well. So if this is the case, you still get the force that is a repulsive force. So you still have the green arrow over here as a force between charge number 1 and number 3. Does that make sense to you guys? And you still need to say the charge number 2 must be positive to give you an attractive force, the blue vector, to cancel out the green vector still. Cool? All right. Or on the other hand, you might just say, well, John, what about if I assume that the charge number 3 is positive, but then the charge number 1 is negative? That is fine. If this is the case, the interaction between 1 and 3 will give you the blue vector. It's an attractive force. Does that make sense? And then it's forced you to conclude that the charge number 2 must be positive because this will provide an repulsive force, the green one, to cancel the blue vector out. So as you can see, and now you can list the last combination if you like. So if I assume that the charge number 3 is negative and the charge number 1 is positive, you get an attractive force, which is the blue. And then it's forced you to conclude that the charge number 2 must be negative to give you the green. All right, and that's conclude all possible of the 4 cases. So now I can erase all these weird looking arrow here. All right, So you guys with me here? So all in all, what I'm saying over here is this problem doesn't really matter what type of charges that you are talking about, because you are pretty much worried about the magnitude. It's going to be Q1 here, it's going to be Q2 there, and it's going to be Q3 here. All right. And then you can play around with the combinations of the type of charges that you want to place, that you want to assign to all these three particles. But anyway, the total thing, the key thing that you really need is the force on particle number 3. Okay, let me write it like this. It's 1, 3. Does this make sense? Or here, this is where the confusion might creep in. I can write it like this. This is a force on 3 due to 1. So I put it as an F31. Okay, and I can do the same notation over here. I can say this is an F3 due to the charge number 2. So I put it as an F32. So as you can see, it doesn't really matter what types of charges you're talking about. It still be the force interacting between the charge number 1 and charge number 3 for the F31. Okay, but it depends on the cases of the it depends on your choice of types of charge, that which one will be 3-1 or 3-2, up to you. But eventually you want two of these vectors to cancel each other out. I don't know, am I explaining understandably or not? But the whole idea is, no matter which type of charge you assign onto all these particles, then eventually you're going to get the final answer anyway, because what we care about is just the cancellation. So what we need is just to say that the magnitude of the charge of the force between 3 and 1 must be the same as the magnitude of the force interacting between charge 3 and 2. Does that make sense?
Okay.
I hope. Okay. All right. So if this is good, then now let's calculate what is the amount, what is the magnitude of the force between 3 and 1. So from Coulomb's law, it's going to be K Q1 Q3 over the separation between those two charges square. With me? And same thing happens to the F32. It's going to be the force between two charges, Q2 and Q3, divided by the separation between those two charges square. Cool? And as you can see, with this equation, you don't care about the sign, right? It's just, the sign needs to be correctly assigned just to make sure that you get the cancellation of the forces. That's all. But at the end, no matter which one of the 4 cases that you pick, you're going to end up with this equation. Cool?
Okay.
All right, I hope this works. All right, so what we have with that is now, hey, one thing from here, it's almost done, right? First thing first, you probably can see about that. I can cancel Q3. I can cancel the K. So your job is almost done. So what they want is the ratio between Q1 and Q2. So I just move R13 square to the other side. And as you can see, the distance from 1 to 3 is twice, okay? They said is L23 and L12 are exactly the same. Let me call it just L then. So that means R13, that is 2L. R23 is just only 1L. Don't forget the square. So the L square cancel, you get 4. So that's it. That is the ratio between Q1 and Q2. Which makes perfect sense. Q1 has to be stronger. The magnitude of Q1 is supposed to be bigger than the Q2 because Q1 is further away. So you want to compensate the further distance by having a bigger charge on it. So that's why Q1 is 4 times bigger, all right? Because it's inverse square law. Okay, does that make sense? All right, Q1 is twice the distance, but because the distance need to be square in the Coulomb's law, so you have to square that and put it on the charge. So the charge has to be 4 times bigger to be able to cancel the force due to the other charge, Q2. Cool. All right, one more thing before we move on to the next one. During the process of doing this, if you notice, I can cancel Q3 out. That's exactly what happens if you would like to think of this particular problem from the perspective of electric field. Cool? Wow. If you want to think about this in terms of the field, it's exactly the same of saying that, well, hey guys, I would like to calculate the ratio of these two charges where the field at point 3 equal to 0. Does that make sense? Let me write it like this. I mean, we just communicate. The sigma E at location number 3 must be 0. Okay, and then now you can imagine that only thing that you need is calculating the field from charge number 1 and charge number 2. Okay, follow me here. So if you want to think in terms of that, I can say that the green vector is just the electric field coming from point charge 1. And I can think of the blue vector to be just the electric field coming from the charge number 2. Does that make sense to you guys? Okay, I should put the arrow on top of all this stuff. Sorry. Okay, with me? All right, so that means I can reimagine everything in terms of the field. By having that, it means I don't really need the charge number 3 there. Cool? And if that is the case, all I need to do is just assuming that the charge on 1 and 2 must be different type because I want the electric field to point in the opposite direction. And all I need to do is just saying that, Ajahn, let's go ahead. I want the magnitude of the E1 to be the same as the magnitude of the field E2. And what is the electric field equation? It's just a K times the charge generating the field divided by the separation, right? Square. It's still the same separation, R13 anyway. Must be equal to the K field from charge number 2. You put Q2 there, divided by the distance from charge number 2 to the location that you want to calculate the field. Square. You see that? This is exactly the same equation as the one that you just saw when you already cancel the Q3 out. Okay?
Okay.
So I hope by doing this problem, I think you guys see the similarity between approaching the problem with the fields, or you want to approach the problem directly to the forces. Same thing. And as you can see, while we are doing this in terms of the field, you don't have to care about the charge Q3 at all. Oh, there's a question come in. Yes, go ahead.
Where is 2L come from? And why 2, 3 don't have square?
Oh, yeah. Oh, sorry. It's supposed to have a square there. All right. First of all, sorry. Yeah. Okay. So I just call this L23 and L12 to be L, just so it's just easier to write. That's all. I assign it myself. Because they said that the distance L12 and L23 are exactly the same. So let me just name it L. That's all.
Here.
Okay. All right. And thank you for that square. You need the square up here as well. Yes. Okay. Very good. All right. I just want to check that you guys still with me or not. Just kidding. Already. Is it done? Okay. It's good. This one. All right. So you can think in both ways. All right. You can think in terms of the force between, every time you talk about the force, you need a pair of charges, right? You need 2 charges and then you calculate the force between them. But if you approach from the perspective of fields, then you only need that, you only need the charge that generating that field. So it's a single charge and the location that you want to calculate the field. But at the end, you get the same answer. Is this a good example? Yeah, I hope so. All right. Okay, keep going. All right, try this one, guys. All right, it's going to be a lot of fun. Woo. All right, I want you guys to try this one because this is the one that is going to be in the exam. I don't have anything else to ask. So I'm just going to put an arrangement of charges, and then all you need to do is just calculate me the net force, the net fields at some particular point or whatever, blah, blah, blah. So let's try this one. So we have 3-point charges arranged as shown in the figure. Find the vector force, right? They want the net force on 5 nanocoulomb. The n there is a nano, is 10 to the negative 9. So it's a 5 nanocoulomb charge. I'm gonna give it a shot. All right, so I'm gonna try to do two ways. All right, so you guys can see and compare. I'm gonna start with the Coulomb's law, which means I'm gonna work on the forces. I'm just sorry. I'm just trying to calculate the force acting on the 5 nanocoulomb charge. Okay, so follow me here. Let's start with this pair. So I'm gonna start with this pair right here. Okay, so it's 5 nanocoulomb is positive, and you have the bottom one, the -3 is negative. So they are going to exert the attractive force on the 5 nanocoulomb charge. You guys with me here? All right. So what I have over here is the 5 nanocoulomb charge will feel an attractive force due to that -3 nanocoulomb charge. Not bad. I'm going to call this F1. All right. And now pay attention to the pair of 5 nanocoulomb and the 6 nanocoulomb. Now they are the same type. They're both positive. So they are going to repel each other. So when we are focusing on the 5 nanocoulomb charge, it's going to be force pointing in this direction. Does that make sense? Okay. All right. It's not drawn to scale here, but all right. I hope it's not too bad. All right. So that's it. Let me call this F2. Okay. All right. Let me put this out of the way here. Okay, there you go. All right. Now, what you can do is calculating the magnitude of each forces. So let's start from F1 magnitude. Use the Coulomb's law, the K, the pair of the charges, Q1 and Q2. I mean, two charges here. So it's going to be 5 nanocoulomb times 3 nanocoulomb. See, I don't need to bring in the negative sign. I don't care about the sign anymore. I'm talking about the magnitude here, divided by the separation. And it says 0.1 nanometer. I'm sorry, 0.1 meter squared. That's it. That's the magnitude of F1. Cool. All right. Try again for the F2. So the magnitude is from Coulomb's law, K, times the charge from those pairs, 5 nanocoulomb and 6 nanocoulomb. So 5 nanocoulomb, 6 nanocoulomb divided by, now the separation is 0.3. Okay. So now you have both forces.
Okay.
And all you need to do is just sum them up in the vector summation way. So what you need is, of course, you need to do the vector summation here, and you need that Pythagorean theorem there, yeah? So the net force magnitude, right? I just only care about the magnitude at this point. It's just going to be the magnitude of F1 square plus the magnitude of F2 square under square roots. So you do Pythagorean theorem, and that's it. All you have to do is just plug in this number, whatever you get for the F1 and whatever you got for the F2. Plug it in here. Bam. Bam. Right there. And that's it. You're done. All right. However, if you do it like this, what you're saying is the vector F total is going to point diagonally down like this, right? Right. Which sometimes just like, I don't know how to tell you the angle. I can calculate you the angle if I want. Yeah, you can calculate the theta from the vertical and horizontal components. But if you still remember the IJ notation, actually your answer is already done. What you can say at the end, you can summarize like this. The vector force is just, look at this, F2 is the one that pointing along the x-axis. So what I can say is an F2 magnitude. And I can say it's in the negative I direction. You guys with me here? Okay.
Okay.
Or it's the same thing as you write F2 and then you say negative I hat. It's the same thing. I mean, you have the vector of the magnitude F2 and it's pointing to your left. And then you say plus, now you just take the F1 magnitude and it's pointing down. So when you say it's pointing down, what I can say is it's negative J hat. Or it will be the same thing as you say is an F1 negative j. And that's it. That is your answer right away.
Okay.
You can use the ij notation to answer the vector force. Or for some of you that are familiar with another notation, but I don't like the ij negative, blah, blah, blah. I know that the F2 is pointing to your left, pointing to the negative x direction. The blue is pointing down, negative y direction. I can also write it like this. You guys do remember the brackets notation? It's going to be negative F2, negative F1. You can use the bracket notation as well. That will do. Okay?
Okay.
And for those of you that still remember a little bit of the vector, this is pretty much exactly the same as this one, even though it's kind of like harder to write on. I mean, it's not harder for us, but it's harder to type in the textbook. Yeah, same thing with this. If you still remember that, sort of like the vector notation in there, when you study like vector and metrics and all this stuff, it's right here. They're all the same. They're talking about the same thing. All right, so you can pick and choose whatever notation that you prefer. I don't mind. They're all the same to me. So same thing goes with, I think that some of you asking about the significant figures in our exam. So I'm not sort of like worried about that at all. As you can see, I very really like slack off in terms of having the significant figure taken care of. As you can see, see that they use like 5.00 nano Coulomb. I just put 5 nano Coulomb there. So I already just, all right, I care only about the, the theory, the understanding of the concept and all this stuff. In terms of the numerical value, we can park it somewhere for now. And let's treat that one maybe in experimental physics somewhere in the lab and on and on. Okay. All right, cool. So is it good? Got the idea? All right. So this is what we have been doing all along. It's just like, oh, Ajahn. All right. So all I need to do is just calculating the force from each pair. All right. So no matter how many pairs you have in your system, you have to calculate all of those pairs and come up with the force vector. And then at the end, all you need to do is just sum them all. Okay. All right. Now, what I can do one more round is this. Oh, I think, I don't have another copy here. All right. Wait. I think I don't want to erase this one. So, is that an option to copy? Duplicate. All right, here we go. All right, lovely. All right, here we go. So I'm going to show you one more time by doing exact same problem, but in terms of electric field. All right, so I'm going to show you right now. Actually, why don't we just start from scratch? Assume that there's nothing going on here at all. Okay, so here, another way of doing this is instead of talking about the forces, you can start by first forget about that 5 nano Coulomb charge right away. Forget about it. Okay, so I'm just going to remove this one from the figure for now. And all you have to do is just calculating the field at that location first. Okay, with me? The field. So let's start from the blue. The blue is negative, so that means the field will point towards it. Cool. Now look at these are orange. The orange one, the 6 nano Coulomb, is a positively charged particle, so the electric field will point away from it. With me? All right, and now I can call the electric field from the first one to be E1, and I can call, I think I use the green color, but it doesn't really matter, right? Let me change this to green. There you go. All right, so let me do the green instead. Here we go. All right, here we go. All right, so what we have here is E2 vector. See? All right, so right now we don't have any charge at the location of the origin at all. So all I need to do is just calculating the electric field magnitude, E1. So once again, for those of you that saw me writing back and forth between the arrow and non-arrow with an absolute sign, I just want you guys to be familiar with 2 types of the notation for the magnitude, okay? So you can write the arrowhead on top with the absolute sign, or you can just drop that arrowhead, and then you just say it's his E1. They're all meaning it's the magnitude of E1 vector. And from this, you can do is a K, the charge generating the field, 3 nanocoulomb, divided by the distance from the charge to the location of the calculation is 0.1 meters squared. Got that? That's the field. And then you do the same thing with the E2. Okay, right, either way you like. It's a K times the charge generating the field, 6 nanocoulomb, divided by this distance from 6 nanocoulomb to the origin is 0.3 meters, and then you square it. Now that means if you add these two vectors together, you will get the net electric field at this point. I can call this a sigma E. Okay. And then we can say the sigma F, which is the net force. Sigma F is just the charge times the field at that location. Okay. So what does it mean? It means I just bring back that chart. But John, let's bring back that thing over here. It's hidden here somewhere. It's like scratch off. It's kind of fun. Okay, here we go. There. It's just like I already calculated the fields, and then I just placed that 5 nanocoulomb charge there. What will be the force on it? Well, John, that's easy. The force on it will be just the charge that you just placed, 5 nanocoulomb, and the electric field at that location. So it's going to be 5 nanocoulomb times the sigma E at that point. And you're done. When you're done, what does it mean by you're done? So if you take these two and do the same thing, the sigma E vector is going to be the green point to your left. Okay, let me just write it as E2. I, and the blue pointing down. J, right? Or if you want a bracket type, it's a negative E2, negative E1. There you go. And then the force will be just exactly that. 5 nanocoulomb times E2. I minus 5 nanocoulomb times E1 J. And you are done.
Okay.
So if you compare whatever you got here and the one that you just got in the previous page, then you will see that it's going to be exactly the same right there. Okay. So I hope by showing you these two approaches, you can start to feel that, okay, no matter what we do, we are going to end up with the same answer anyway, because field and force are connected by just this expression right here. It's just, once again, mg. Oops, sorry. It's mj, right? When you know the field g, place the mass m in there, you can calculate the force. So if you have the field E, you have the charge Q, the force is QE. Same thing, exactly the same.
Okay.
Cool? Very nice. Okay. All right. So I hope this is very good. And I hope it's summarized things that we have been doing up to this point. All right. Just to make sure that you guys understand how things goes. Now we're going to bring you up another notch here. Next one, guys. Give it a shot. Woo. All right. Now this one gets more complicated. Now you have 4 charges now. All right. And the question asking you to figure out the net force on the particle number 3. Now you have a choice. You can do with the Coulomb's law, starting calculating the force on each pair. 3 and 1, 3 and 2, 3 and 4. You get the 3 vector forces. And then you just do the summation on those. Or you can also, forget about the charge number 3 at the moment and calculate the field due to the charge number 1, number 2, and number 4. And then once you get those electric fields, then you just multiply by the charge number 3. You get the force as well. Like that. Okay, want to give it a shot right away? All right, okay, let's do this together. let's do the votes. Do you want to go with the fields or you want to go directly to the force right away? There's like some interactions here. Probably there's none. All right, well, Dan, just do it. I'm just watching whatever you're doing. Don't have to ask me. All right. So, hey, I want you to vote, not just laugh at me and you guys. Okay, so you want me to show you the field approach or you want the force approach? Or some of you will say, just do both, Dan, so you can take a lot of time and I will go somewhere else. All right, okay. So if you're not saying anything, then I'll do my preference. I love to do the field, all right? And I will calculate the force at the end. That's my way of doing it all the time because it's annoying to me to do the force on each pair all the time because you have to care about what this started. I mean, it's not that annoying, but for the problems that I mean, when the system is not that complicated, it's just easier to look at the fields due to the environment first. And once you're done with the field calculation, you just drop the charge at that location, bam, you get the force at the end. It seems easier that way. But I mean, the idea of force is not that bad. The crazy idea that you might have not think about is when you look into a crystal, like the one that you may be familiar the most is like the salt crystal, the sodium chloride, the sodium chlorine ion and all this stuff. You have the sodium ion and the chlorine ion, and all those ions are just like, you know, crazy amounts of those. And every time that you want to calculate maybe the stress between them or what is the energy between those, usually you have to calculate in a pair because you want to know, hey, okay, you have a pair of this, and then you have to do like Avogadro number of those. And at the end, you arrive at the total internal energy of the whole crystal, on and on. And that in that case, then, all right, I don't mind doing a pair and what is going on each pair because I want to sum them all. But for the system that's so pretty much like, it's still called simple, you only have 4 charges and you want to know what is going on with the charge number 3. I'll calculate the field from the first 3 charge first, and then I drop the last one on and calculate the force. Yeah, sounds cool? All right, so I'll go with that.
Okay.
So go ahead. E1, the Q1 is 100 nano Coulomb. So it's a positive charge. So the electric field will point away from it. There you go. All right, let me name this E1. All right. Now Q2. Q2 is negative from the look of that one. So the field will point towards it. With me? All right, I can sort of draw dot. There you go. So because Q2 is negative, so the electric field will point towards it. Very good. Now, what about Q4? Q4 is also negative right there. All right, so that means the electric field from Q4 at location number 3 will point towards it. There you go. Let's do the blue. Cool. That's it. So you have already 3 electric fields. And now I can name this one. Okay, each one of them, let me name this E2. And let me name that one E4 then, just to make it coincide with this whole thing here. All right, and all you have to do is just find the net electric field. So what you really want to do is just sum all these vectors together. All right, this one, let's do it color coded here a little bit here. So all you have to do is just sum all these vectors together. But the way that you sum them, you can do the same trick that you did all along. Just you can break the E2 into 2 components if you want. You do the horizontal and vertical component there. With me? All right. So with that, you know that the angle over here is 45 degrees. So you know that the one that is pointing up is going to be E2 square root 2 over 2, right? It's just E2 sine 45. And you also have the horizontal component of E2 root 2 over 2 as well. Okay, so I'm going to give you the overlay of everything that is going to end up with. You're going to say the net electric field vector is, start with the X component, the horizontal component. You're going to have root 2 over 2 E2 That's from the horizontal components of the E2, the green one, plus E4, magnitude. As you can see, this is all magnitude. And this whole thing points in the positive X direction. Cool? No, okay?
Okay.
And now look at the vertical direction. The E2 root 2 over 2 is pointing up. So I can say it's root 2 over 2 E2 is pointing up. Then you have E1 pointing down. So you do minus E1, and the whole thing is pointing along the Y direction. So it's a J hat.
Okay.
That's it. You're done. You already got the electric field at the location of charge number 3. And your task is just, Bajan, all I need is just E1, E2, and E3, E4. E1, E2, and E4 magnitude. Bajan, that can be done very easily. The magnitude of E1, all right, look at that, is the K times the charge generating the field Q1 divided by the distance square. And just plug in the number. All right, just to show you, I think maybe this is a good example to just give you a number. All right, I'll just omit the unit for now because ran out of space here, but that's what it is. Nano 10 to the negative 9 divided by A, which is 5 centimeter. So you can say it's 0.05 meter square. Here we go. All right, I'll just put nano is a Coulomb there. And the K is the unit is long, so I just omit that, but there must be some unit there as well. All right, so that's how you calculate the E1 magnitude. And you move on to the E2. It's going to be the K, the Q2 over, now you want the distance over here. You want the whole diagonal distance over here, and it's just root 2A, the whole thing square. With me? Okay?
Okay.
And all you have to do is now plug in times Q2, which is 100 nanocoulomb, same value, divided by root 2 0.05 meter, the whole thing square. Cool?
Okay.
All right. And then the last one, the E4 magnitude is K times the charge times the separation, which is just A square. All right. I think you can do the substitution yourself, but over here is 200 nanocoulomb divided by 0.05 meters square, and pretty good. You got all of those. I think this is supposed to be positive. All right. So you got all of these value of E, E1, E4, E1, E2, and E4. And then you can put it in a vector format as well. Everything is good. It's done. So you know everything about the electric fields at the location of the charge number 3. Now, the last step is a super simple one, but you want the force total on the position, on the charge number 3 that you locate at the location that you're just calculating the fields, just multiply that. So you take the Q3 and you just multiply by the sigma E that you just got. And you just throw that sigma E there, here. And that's it, guys. You are done. Isn't that nice? Cool. All right. So it's just like you pull a common factor Q3 out. You can think of it that way. It's just like, because if you want to do the force approaches, do you want to do the force approach? It's just, well, you have to do the Q3 with the Q1, Q3 with the Q2, Q3 with the Q4. And it's just like you pull a common factor Q3 out. And the rest of that is just electric field. Same idea, right? What else could it be? Right? Nice. So I hope this helps summarizing everything that we have learned about the force and the fields and the connections between the two. And I just want to emphasize, I don't know, I'm emphasizing this enough, that those two are super, super duper close in connections. Once you know the fields, place the charge there, you get the force. Done. Very nice. Any questions so far? Cool. All right, very nice. So if this is good, I think this is a good place to stop. And for the rest of today's lecture, the other half, we will bring you guys to, well, I don't know, to what? To the stuff that need to be done in the college physics, which is the calculus-based problem. And now it's time for us to do a very fun integrating calculus. That's right after the break. We'll see you in a bit.
Okay.
Wait for it, guys. One first. All right. So what we are going to do next? I think maybe I mean intentionally just only to include this sort of like integral calculus just for this portion, just within this portion of the course only, because I don't want you guys to, you know, worry too much about have to do the integral here and there back in the day of the thermodynamic stuff or in the oscillations and wave stuff, because, well, I don't think we need a lot of this. However, we need some of this.
Okay.
So if you haven't seen this kind of thing before, it doesn't seem like we are doing college physics at all. So that's why I decided to include the vector calculus and the integral calculus within this portion, which is, I think, is understandable, because in reality, this is the stuff that we're going to deal with, because it's kind of hard for you to have the situation where the charged particles are arranged in, like, you know, dot here, dot there. There's like a 1 point charge here and there. Usually they come in like a jam-packed, like, I don't know, you think of it like you talk about a material, and then you know that you're going to have like a million electrons running around, million ions running around. So if you zoom out and you look at that system in the macroscopic level, it will look continuous to you. It doesn't look like a point charges lying here and there, but it's going to look like a continuous charge distribution. And that's when your calculus will come into very handy, because that will allow you to manage. Here, you have a bunch of charges over here that you don't want to deal with them individually anymore. You can assume that these charges are arranged in a continuous fashion. Nice. And the question stays the same. You are at some point P away from this charge distribution, and you would like to just ask, well, John, I still want to figure out what is the electric field at point P. So the idea is going to be very straightforward. Well, if you can, you think of 1 point charge within that continuous charge distribution, and then all you need to do, just calculate the electric field due to that tiny piece of charge. And then you move on to the next piece. And then you do the same thing. Well, hey, what is going to be the electric field at that point? And then you move on to the next one. And hey, what is going to be the electric field from that point? And then you move on to the next one, on and on. You see the progress that we have to make here? It's going to be like a lot of this. All right. But the idea is very simple. It's still, you do the sum, you add them all, the electric fields from each individual tiny bit of charge. So you can usually call that bit the delta Q. Does that bring back the memory here?
Okay.
So now you start to think of like calculus. Now here we go. Delta Q is here. All right. So that's what it is. So the idea is you slice the charge distribution into a tiny block yourself. See, you know, okay, just consider like a tiny piece of charge. And within that block, you should contain a little bit of charge. That's the delta Q we're talking about. And all you have to figure out is what is going to be the distance from that block to the position of the calculation. And if you call it at, it's still R. The electric field that you got from that tiny block is going to be K, the charge generating the field, delta Q, divided by R squared. See how easy it is? I haven't done anything new. It's just KQ over R squared, but the Q is just delta Q in magnitude. And because this electric field is going to come in a very, very small amount, so you put a delta sign in front of it as well. All right. And once you keep doing this, you just move on to the next block, move on to the next block, you move on to the next block, you move on to the next block, just like what I just did in a red dot over there. And then just calculate the electric field here. You calculate electric field from there. So this means you're going to get a bunch of those electric field from all those blocks that you just slice from your charge. And at the end, you just have to sum them all. Sum them all. And that's what you get as this expression right here. See, that's easy. All right, the concept is that it's a sum of the KQ over R squared, but the Q is just a tiny Q, delta Q on each block. So when you do this and you want to make things smooth, you don't want to block anymore, you want things to go smooth, you take that block and say that that block approaching zero, zip nothing, you're supposed to make it shrink down to a super, super tiny stuff. So the delta Q that you squeeze in that box will turn into just a differential Q. Does this ring a bell here? And of course, in the limit of delta Q approaching zero, your delta Q will be written in terms of the dq. That's your notation back in the day of the calculus there. And then you turn your summation into an integral. And that's how you manage to calculate electric field from a continuous source cycle. All right, it sounds easy, of course. I mean, Ajahn, you just write down the formula. So the hardest stuff for this particular problem is how. How are you going to apply this equation to a real problem? Okay, so that's the business that we are going to deal with today. Okay, guys, don't worry. I'm not gonna go crazy like him. I'm not gonna give you like a super complex setup for you to calculate the electric field. No, but I think you need to be able to calculate some simple geometry of the charge arrangement. That's all I'm asking. All right. So don't worry that you're going to have, integrate like, maybe like what, like a triple integral. You're doing it like, no, don't worry about it. Okay. You're only going to do a couple of geometry that I'm going to give it to you as an examples anyway. So we are going to go through all of them together. Plus, because even though I don't give you a complex system, it's going to be complex already. Because what you are dealing with over here, I don't know, have you noticed this or not, is the integral, but it's the integral of a vector quantity. Remember the annoying r hats that we had before? The r hat is just a vector that's point radially outward, right? But here, the idea is you do the integral of the vector's quantities, guys. So this is not the integral of x, you get x squared over 2, not yet. You need to determine them in the vector fashion first. And then eventually at the end of the road, you might go back to do the algebraic integral. Cool?
Okay.
All right, so make sure that what you're thinking in your head is the vector summation, but you do summation in a continuous way, so it turns into an integral. All right. And what you're doing right here, this is vector calculus, guys.
Okay.
And for those of you that already took calculus 4, this will be familiar to you. All right, guys. So let's give it a shot. So I think I'll show you today maybe 3 examples. 1, 2, 3. All right. Just these 3, I'm done. I think this is more than enough for us to learn. And I don't think we need more or more complicated setup. So I'll show you the line, how to calculate the electric field from a line charge. Okay. Or maybe it's a charge on a rod and a ring of charge and an arc, right? You have a bent plastic, like a rod that bends in a portion of a circle, an arc, a circular arc, and then you want to calculate the electric field at the center. All right, I think these already good exercises. Okay, let's start from the first one. I think you need to imagine this along with me. Okay, now you have a rod, and this rod somehow get charged. So it means you sort of like sprinkle around with the electrons or whatever the charge on there. And it turns out the total amount of charge on here is equal to Q, the net amount of charge. Distribute uniformly across. So when you have a uniform distribution, what you can do is you can just assume that all the Q is being spread around uniformly. So it means no matter you cut this rod out, you get the same amount of charge per unit length. Cool? Got that one?
Okay.
All right, keep going. Now calculate the electric field at point P, which is located along the long axis of the rod, which is the figure already portraying that. And the distance from the left end of the rod is A. So they want to know what is the field at that point P due to the charge that distribute uniformly on this rod of length L. You want to give it a shot?
Okay.
No, probably I have to start this one first. Okay, the idea is this. Based on what we talked about here, you have to slice your charge distribution into a tiny bit first at a time. So this is how it's done. So I'm going to slide this into a tiny piece. This is supposed to be super small. When it says super small, mean it will take up a little bit of space, dx. Because as you can see, the layout of this one, you already put the rod in along the x-axis. So when you cut or slice the rod into a tiny piece, it will take up a little bit of space. Let's call it the dx. All right, it's approaching 0. Okay, and then of course, within this, you will say it will contain a little bit of charge. Let me call it dq. Does that make sense? Okay, it's a tiny charge that you slice out. So that means, think of it in your head, it's like you have the dq charge within the length of the rod of dx. So I'm asking you a very simple question. What is the electric field due to this dq at point P? All right, simple. Electric field from the formula is the K times the charge generating the field divided by separation square, correct? That's what I want. So you say it's going to be K. The charge generating the field is nothing more than just the dq that we slice out, divided by now the distance from the dq to point P. Look at this one, Ajahn, because the figure already nicely placed the rod and point P very beautifully in the sense that point P is already located at the origin. So good. So all you need to do is now the distance is automatically is your coordinates of that dq. All right. So if you know the position x of that dq, x is going to be your distance from that dq to point P. So I put x squared on it. Cool.
Okay.
And because this is going to be the field coming from a super, super, super tiny charge dq, let me call this dE, shall we? And that's it, guys. That's the first step. Very cool. All right. What is the next step? Well, Ajahn, you have to keep doing this. What do you mean? You have to slice a tiny dq here from the left end of the rod. And if you keep doing slice, another slice, another slice, you slice, 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 slice. And each slice, you have to do this kq over r squared. You guys with me? Okay, come along with this. For example, if I do the left end slice, I'm going to have dq on here, right? The dq will generate electric field dE. With me? And then I move on to the next slide. So let me use different color here. I'll move on to the next slide. In the next slide will contain the charge dq as well. And it's going to generate another dE. It still point to your left. And if I move on to the next slide, it still contains dq as usual. But then you're going to generate another kind of dE. I mean, not another kind, another value of the dE, k dq over x squared. And you just keep doing the next one. It still have the dq on it. Okay, and then you're going to generate another dE. See, you have a bunch of dE that you need to sum. A lot of dE due to each segment of the dq that you slice out from this. And the net electric field that you're going to get at the end supposed to come from this sum of all those dEs. With me? But when you do the dE in the differential form, it's infinitesimally small, super, super duper duper small. That summation turns into integral. And that's exactly what you did back in the day. All you need to do is just integrate this. With me here? The reason this problem is still simple, you see this? All of the dE that you got from the dq inside the rod always point to your left. They're all pointing in the same direction. So what does it mean? It means the expression that we got here, k dq over x squared, can be used to describe the field comes from all those dq on the rod. And all you have to sum, turns out that this summation, even though it's the vector summation, but it's still down to only a single component. So it's a single component sum. See, everything is just pointing to your left. So it's a negative x direction summation. So that's why, even though it's a vector in fundamental, I mean back in the foundation of this whole thing is a vector quantity, but they're all pointing in the same direction. And all you need to do is just take the sum of all those numbers. That's why your integral is still look algebraic sum. It doesn't have any vector on it, but even though you know it's all point in negative I direction. That's in your head. With me? All right, but all you need to sum is this sum here. Is the integral, sum mean integral, the integral k dq over x squared. Okay, I'll just keep writing, yeah? So this is what you want. The net electric field will be integral k dq over x squared when x start from the left end of the rod right here, when x equal to a, and then you're going to do the summation all the way when you slice out the last piece of this rod, which is the right end of the rod, when x equal to a plus l. You're almost done.
Okay.
Cool? The reason I say almost done because you cannot do anything much right now because the function that you want to integrate is k over x squared. But the variable that you have in here is q. They are not the same. When you do the integral, the function of integration and the integrating variable must be the same. So how can you turn q into x or you turn x into q? And now the word uniform comes into play. All right, now almost done, guys. Stick with me here. Look at this a little bit. You said when you slice a piece of the rod, it takes it take up the space of dx. Within that dx, you contain the charge dq. But we already said the total amount of charge q distributed across the rod uniformly. When you say uniform, it means no matter which place on the rod you're talking about, the amount of charge per unit length must stay the same. That's guaranteed the uniformity of the charge distribution. You guys with me over here?
Okay.
So that means if you take the whole rod, it's going to be Q over L. That's the density. Now you start to talk about the density. And the density come back again. So the density of charge, which is the charge per unit length, is a one-dimensional density. Remember we used this before? Because we don't have any width, we don't have any depth, it's only have the length. So you only have a single dimension to talk about. So the density is charge per length. Let me call this charge per length the lambda. That's a linear charge density. But then no matter what you do, if you look closely over here, Ajahn, I can do that things as well in the infinitesimal way. Is a charge per length. So it's going to be charge per length. With me, guys?
Okay.
Must be the same because the distribution are exactly uniform. So no matter which part of the rod you're taking the density calculation, they must have the same number, lambda. So this allow you to get this relationship over here. It means you can always talk about the amount of charge by taking the density lambda and multiply by the length. Isn't that simple?
Okay.
Okay, one more time. Think of the density in a natural way. But hey guys, I have a charge of 1 Coulomb per meter. 1 Coulomb per meter. That's my charge density. So if I bring in a rod of 1 meter, I definitely get 1 Coulomb. If I bring in 2 meter, I'll get 2 Coulomb. I bring in 10 meter, I get 10 Coulomb. I bring in dx meter, I will get dx Coulomb. Does that make sense? So the way that you get to the charge is simply take the density multiplied by the length. You get back the charge. That's it. So that's how I'm going to be able to turn this into lambda dx. Nice. And now with that, I'm doing the integral on x from a to a plus l. Due to the uniformity, lambda is constant. I can pull lambda out from the integral. K is definitely integral, is a constant already. So what you have to integrate is this. 1 over x squared from a to a plus l. Almost done.
Okay.
Everyone knows how to do this. 1 over x squared integral, you get negative 1 over x from a to a plus l. And that's it. It's a lambda k 1 over, okay, it's a negative sign. So let me put 1 over a first and 1 over a plus l. And that's it, guys. You
Okay.
not bad. Okay, I can rearrange this one to make it look a little nicer, but I mean that not much can be done further now. It's just like L over A plus L. I mean, it's just the manipulation of the form, but that's not done. And with this, I can say I can turn this into vector right away by just put the arrowhead on top and say it's negative I. It's just going to point in my negative X direction.
Okay.
How do you feel? It's kind of doable. I would say this is maybe almost the hardest part of the course now. I still have one more, right? I think that's the peak of the course is after this one, right? This one is almost there, but it's not too bad. I think if you practice for a couple of exercises, I think you get a clue. All right, but let's do it. If you still sort of like, okay, then I kind of get it, but it's still, all right, I'm not sinking everything into my brain yet. So try this one, more challenging. Now you have a ring of radius A, carries a uniformly distributed, one more time, we love uniform distribution, positive total charge Q. So this means the total charge on here is Q. Calculates the electric field due to the ring at point P, lying on a distance X from its center along the central axis perpendicular to the plane. So this means it's right on the central axis. That's what it says. It looks complicated, but you will see at the end, it's actually easier than the previous one in terms of the calculus-ish stuff that you have to deal with. But in terms of the setting up of the problem, this one is harder. Okay. Stick with the plan. The plan is you have to slice your charge into a tiny piece of charge yourself. So let's do that. Bam, I slice it out, a tiny piece. Within that piece, it contains a little bit of charge in there, dq. Cool? So I'm asking you the same question. What is the electric field due to this tiny piece of charge dq at point P? You say, but this is not bad. I can do that because the electric field coming from the dq, we always assume everything is positive in the first place at this point. And we're going to generate electric field pointing away from it. And because that is a tiny charge dq, I'm going to say this is a tiny electric field dE. So the dE magnitude is K, the charge generating the field dq, divided by the separation from that point to the point P, which is, they said is R. Let's put R in there, R squared. That's it, you're done.
Okay.
Everyone now knows this is the magnitude of the field due to that tiny piece of charge dq. And if you put it in a vector form, it's going to point diagonally down like that, right? But then you have to do this everywhere. You have to slide this to the next one, slide the next, until you go around the ring, complete the whole loop back to the top part of this one. You guys with me here? You have to slide, right? Now you start to imagine everything in a vector form. And I have to ask for your imagination now. You think about the dq. I think maybe the best way to compare this one is if you look at the opposite end of this one, if you do the dq in the bottom, the dq in the bottom over here will generate the electric field point diagonally up. You guys with me? Okay. So imagine this. You have to do this all around. When I say all around means, if you imagine that, okay, let me write it like this. If I do the slice on the front and the back end of this one, it will generate electric field 0.2. I mean, it's sort of like a little into the page and a little out of the page. I don't know. Can you imagine it? I don't know. I'm drawing this in the perspective form correctly or not. But the whole idea is this. If you start from the dq from the top and then you start rotating the dq around the ring, you will eventually generate a cone of the dE. You guys with me with this? The blue is on there too. Okay. Start to see this? You wrap around, you slide the dq around the ring. It will start to generate dE. The dE will start to move. Okay. Not move, start to show up, and it's going to trace a shape of a surface of a cone, those dE vector will be on the side surface of the cone. Cool? And then what you need is you want to have this all sum up into your net electric field.
Okay.
But Ajan, can we do this? Well, yeah, this is not bad, because imagine this. If you kind of like have that imagination already built in, think about this, comparing between the topmost DE, the red, and the bottom down there, DQ in the blue. If you just only compare about these two, I mean, you try to find the net vector summation from these two vector, you can do it using the component analysis. You guys with me here? And then you do the red one, component. And yeah. So by breaking the electric field dE into the vertical and horizontal components, you start to see that, oh, John, this vertical component will cancel. So that means the one that you try to rotate until you generate a cone on this, the vertical component will generate a circle. With me? So this means on this circle, the perpendicular component of all those dE will eventually cancel. They all cancel out. The only thing that left for you to integrate is the one that actually pointing in this direction right there. There will be a bunch of this waiting for you to sum. So this is what you have to add. Add these together. Cool?
Okay.
So that's why what I want, it turns out the net E comes from dE along the X component. That's what I want. I only want the X component, which is the along the axis component of the dE. And all I'm gonna do, I'm just gonna sum them up. Okay. So I hope you understand the whole explanation over here. So come back now. I don't want this anymore. I think everyone's follow here. So that's why I only need this component dE in along the X, because I know along the perpendicular direction will cancel themselves out. There's nothing left there. So what I have over here is dE along the X direction is just the dE, the original dE that we have over here. And then if you say, hey, this is your theta, this must be theta, it's going to be dE cosine theta. This is all you need to sum. I want to sum all this together. Eventually, I'm going to get the net electric field along the E, and I am almost done.
Okay.
How much? Let's try plugging it, plugging numbers in, I mean, the value in, shall we? All right, dE, I already calculated. It's this value here. So it's K dQ over R squared. What about a cosine? Well, cosine is like X over R, is adjacent over hypotenuse. That's fine. Is X over R. That's for cosine. And then now you say, but do we need to integrate this? Of course, we have to integrate, but I mean, once again, do we have to have problem here because the dQ is not the same as the function of R or the X or whatever, right? And then, I mean, are we going to do like a double integral along the ring, blah, blah, blah? No, wait. Look carefully here, guys. Let's keep doing it. Pull out the constants. K is constant. What else is constant? No need a motivation here. What else? Even though it looks complicated and the problem used like X, R, or whatever, but wait a second, Ajahn. X is constant in this one because it's a distance from the center of the ring to point P. So actually I can pull out the X. And once the X is constant, A is also constant, the radius of the ring. R is constant. Oh my God, so nice. So you don't have anything left to integrate except just the dQ. What is the sum of the dQ? It's just the sum of all those tiny charges, and the sum must add up to the total charge on the ring. And that's it, guys. That is your answer, and you are done.
Okay.
Good. So see, the difficulty of this problem is not in the integration, but it's in the setting up of the vector summation. And this is what I'm saying. What you're doing over here is the vector calculus. It's not just like, hey, have a function thrown at you and then you do what is the integral of this function? No, you have to determine the vector quantity first. And once you know the nature of that vector quantities, you have to come up with the way that you can manipulate them in a vector fashion yourself. Nothing else can be done more than that. Okay. And integration actually comes at the end when you're already figuring things out about the charge, about the vector directions or cancellation of this and that. And then you have something left for you to integrate, and you do integration. Isn't that neat? All right. Just to practice, all right, from just only these two problems, I want you to look at the last one of the day. If you can get this one, I think this is it. All right. I said, I don't want anything further than this for you to think about. And I don't want you to worry about like a super complicated setup, just only this. And then I will give you some homework problems to try a little bit more, maybe 2 or 3 more setup. And then I think you're done. You're already in good shape. All right. We are not torturing you with the calculus or anything. Okay, try this one, guys. Last one of the day. All right, I think you already, maybe it's already too much, right? Once we have calculus in, that's it. Party is over. Figure shows a plastic rod having a uniformly distributed charge Q. Once again, all right, it's negative. All right, so that's good. The rod has been bent in a 120-degree circular arc of radius R. In terms of the Q and the R, what is the electric field due to the rod at point P? All right.
Okay.
Want to give it a shot and see how it goes? What do you think? It's not bad, I think. Right? Do the same thing. We do this all the time, starting by slicing a tiny piece coming out from this rod. That tiny piece will contain a tiny amount of charge dq. And it might take up some space. That space, because it's an arc, let me call it like a ds or something, right? It's not x, it's not y. It's just an arc length. Let's call it a ds. Okay. So now what you have to do over here is analyzing this dq is simple because once again, you can figure out the electric field due to that tiny amount of charge. Because this charge is negative, so electric field point towards it. With me? Okay. And because it's a field that coming from a tiny charge, you can call this dE if you like. So the dE, all right, this is a vector, but the magnitude of the dE is going to be k dq, the charge generating a field, divided by the separation from the dq to point P, which is just the radius of the rod squared. So cool. That is pretty much done.
Okay.
No, not done. I mean, but that's done for the dq charge generating the field dE. Nice. But what happened next? Well, John, you really have to do this from the topmost. dq, 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 all the way down to the bottom. So each one of those will generate dE, 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 dE. I'm just kidding you guys. All right. So the point is, it will have a bunch of these DE generated all the way down to the bottom. Okay, let me write just a few of those. Just give you an idea. Oh, the size is not so great. Okay, let me try to draw them about the same size. So, okay, here we go. Here we go. All right, but you're going to have all of them there. All right, so all of them is going to spread around this arc right there. You're going to have a bunch of DE pointing out. So you use the same trick, Martin. Let's do the same thing. That DE, let's focus on the red. I can split the red DE into horizontal components and vertical component. You guys with me? When I do that, the vertical components will cancel themselves out one more time. The reason is because you have the same amounts of the one that is pointing up and the one those are pointing down. Cool?
Okay.
It's when, I mean, speak another the way is the symmetry of the problem. You have the mirror image around the x-axis, right? So whatever that's pointing up, you're going to have the same amount of thing that's pointing down because it's a mirror image around the x-axis. Cool. So if I'm going to do this, just to highlight this one, let's look at the blue. If I split the blue, I'm going to have horizontal and vertical component. So when you look at the blue and the red, see, you get the cancellation of this pair. And because you always have a pair, one pointing up, one pointing down, one pointing up, one pointing down. So the vertical components will cancel to zero. So once again, what you care about is we are going to care about the only the x component survive. Cool. You only have to talk about the DE in the x direction. And all you have to do is just sum all those. So the net electric field will be the sum of those DE along the x direction. That's all I have to do. But then you already knew the x component can be done by, okay, DE along the x is just DE. Now you have to come up with the angle. Let me call this angle theta. So it's going to be cosine theta. So it's going to be integral of DE cosine theta. Is it cool?
Okay.
Oh, that's a wrong effect. Sorry. All right. But that's the DE cosine theta that you want to sum. You're going to have a bunch of these DE cosine theta, right? A lot of those coming out of this, coming out of that. Everything just pointing along the x direction. Sum them all. All right. Now let's substitute the value in there. You already calculated the EE. I just plug it in, K dq over R squared cosine theta. Now, the same trick as before, but well, it might be easy. Let's pull out the pull out the constant first. What are the constants here? K is constant. Very good. R is constant. I can pull out. But then cosine theta, I cannot because theta are not exactly constants. Theta depends on, it's sweeping, right? You start from here, you go up there. So the theta changing from down here all the way to up there. So theta is a variable. So you cannot take it out. So that's it. This is the integral that you need to integrate.
Okay.
Okay, cosine theta, sorry. Yeah, okay. Now it's time for us to deal with this conversion of the parameter one more time. I want Q to be expressed in terms of the theta now. So I can keep going. Okay, how? All right, this is going to be the one that, I would say this is stuff that is new here. And I don't know you like this or not, but I have to explain this to you a little bit further here. So let me add, I need an extra page here for that. So here we go. So when you think of this arc, okay, here, I'm blowing this thing super big here. You slide this piece into a tiny stuff, right? DQ is in here. It take up a little bit of length, ds, right? This is a zoom in of this portion over here. That's a zoom in there. Okay, so this is it. But then if you look here at toward the center of this ring, okay, all right. So everyone knows that, this ring down here we go, there. This is theta, right? But when you have a little bit of the thickness here coming from here, it will take up a little bit of the change of the theta. You call it the d theta. Does that help? Right? So that's what you did. Theta is the angle. But when you change by a little bit, you call it the d theta. Okay. So what is the relationship between the dq in here? This is the amount of charge. Okay, let me put it on the side here. The dq is in there. The arc length ds and the subtaining angle d theta. But Ajahn, I still remember the relationship about the arc s, the radius r, and the theta. You already said the theta is the s over r. That's by definition of the angle, right? We learned this one from oscillation, circular motion, and everything. So what you want is just a tiny change in the theta. It's going to be a tiny arc length over the radius. That's exactly what we have over here. Yeah? And that's what it is. So this means ds is RD theta. You can turn ds, turn mean you can link between the ds and the d theta by multiply by the radius. But then, Bojan, we still want to get to the q. All right, q is here because remember, it's a uniform distribution. So if you have the length, you want to get to the q, you have to multiply by what? What? Charge density. So if I want dq will be lambda ds. Okay?
Okay.
So with the lambda ds, just like before, we have the lambda dx before. You want the charge, you take the density, multiply by the length. Same thing. So that's it. So what we have is a lambda RD theta. That's your dq right there. Now take that, bring it back here. So this is what you're going to do is k over r squared integral of the cosine theta. dq is just what we just got over there, lambda RD theta. And you keep going. You do the integral, whatever constant you pull out. Lambda is constant because of the uniform distribution. The r can cancel one of these two. So you're left with just r in the bottom, just only single r. And now you only have to integrate cosine theta, guys. Isn't that cool?
Okay.
And all you have to do is just set up the limit of integration properly. You want to start from the bottom over here, and you do the integration from here, all the way when the theta hits the top of that. Because they say the arc length is being bent in a 120 degree. So you start from down here, that must be negative 60 degree, and you go up there to positive 60 degree, right? Because you use the x-axis to be your 0 degree angle. So that's fine. So you take the theta from negative 60 to positive 60. Isn't that cool?
Okay.
And now everyone knows how to integrate cosine theta, I hope. Yeah, integral of cosine is sine theta. And you set the limit there from negative 60 to positive 60. And cosine 60 is root 3 over 2. All right, let me do it until the end. So everyone's sort of like see the whole picture here. That's the upper limit, root 3 over 2. Subtract the sign of the negative is a negative sign. So it's a negative root 3 over 2. So that's it, guys. It's root 3 k lambda over r. And that's your
Okay.
net electric field at the origin. And if you want to put it in the vector format, it's just the sigma eta we just got, that root 3k lambda over r in the direction. And you are done.
Okay.
Woo. All right, I know you guys, I think you have to go back and maybe revise this one more time. All right, or the best is, if it's possible, then you have to do it yourself without looking at whatever the lecture or anything, and just try to do it yourself, right? You have to test it. If you start from scratch, can you run everything down to the end or not? That would be the best way to practice. But I think by doing these 3 problems, I think this is enough basics for you. And I think it's a good enough background to attack the problems at the level of difficulty that I'm just going to pick and choose for this course. All right. We don't want to go too far, but I think you need to know a little bit of this. You need to do the connections from calculus to the physics, which is, I think, is an application of calculus, I would say. Nice. All right, guys. So that is it for today.
Okay. Okay.